So we start chapter 9 with this lecture, which is about RLC circuits, or specifically second order transients, which means that circuits that have two energy storage elements. And we'll focus more on circuits that have one L and one C. We'll really not talk much about two L's or two C's. There may be some homework problems which will address such a circuit. Okay, so we start with this rather one of the simplest and perhaps one of the most important RLC circuits. It's called a parallel RLC circuit because it has an R, L and a C in parallel. This circuit is extremely widely used in communication receivers. We may talk about the applications later on. Here we just want to analyze. So there is a switch and the switch is closed so that this current source is connected to the RLC network, and at t equal to 0 the switch is opened so that the current source is removed from the RLC network. So what will happen is for t greater than 0, initially there will be some energy in the inductor and capacitor, we'll see where, and that energy will slowly dissipate, and we want to see what is the mathematical behavior of that dissipation of energy via the voltage and the currents. All right, this ground is included only because, as we have seen before, when the switch is opened, we don't want to leave the current source open circuited because that's a conceptual and theoretical disaster. So to prevent that disaster, we connect the switch to a ground so that the current source can keep forcing its current from ground to ground. So the question we are asking is, find this voltage V. There's only one voltage in this circuit with respect to ground. So find that voltage and the inductor current and the capacitor current. And we'll assume that the circuit was in DC steady state for t less than 0. Alright, so as we've done in the last chapter, we'll go through 3 steps solving the circuit for 3 different time regions. So the first thing we'll solve for is t less than 0. So you assume that for t less than 0, the circuit is in DC steady state. So the inductor behaves as a short circuit, the capacitor behaves as an open circuit, and we find so we want to find, what do we want to find? We want to find the inductor current and the capacitor voltage for t less than 0, because as we've seen before, those are the only 2 quantities that will not change when the switch opens. So the inductor current is I0, I've written already. How is that? The entire current I0 flows through the inductor because the inductor is a short circuit. Of course, nothing flows here, but nothing flows through the resistor because the resistor is connected in parallel with a short circuit. The other thing we want to find is the capacitor voltage, which is nothing but V. So how much is V in this circuit? It's kind of obvious. There's a short circuit here. So V is simply 0. Then we say, okay, so that's step 1. Step 2 is solve the circuit at t equal to 0 plus. So I have drawn the circuit here at t equal to 0 plus, and as we've seen before, at t equal to 0 plus, the inductor acts as a current source, the capacitor acts as a voltage source, but we already know that the voltage source value is 0, therefore this will be a short circuit. So this is the circuit at t equal to 0 plus. So in this circuit, of course, V is still 0 as it was before. IL is still I0 as it was before. We also have been asked to find IC. So we need to find the initial condition for IC. So how much is IC in this circuit? So IL is I0. How much is IC? So actually the voltage is still 0, V is 0, so no current flows through the resistor. So this entire I0 flows through the capacitor. and because of current is flowing up in the capacitor, IC will be minus I0. Alright, so IC at t equal to 0 plus is equal to minus I0. So that is t equal to 0 plus. And now the main thing, t greater than 0. So this is our circuit for t greater than 0. Again, as I said earlier, there is no source of energy in this circuit. So this circuit eventually is going to have all zero currents and voltages, eventually meaning at t equal to infinity. But initially it has some energy. So incidentally, where is the energy? Let's go back here. So initially the capacitor voltage is 0, the inductor current is I0. If the capacitor voltage is 0, it has no stored energy. So at t equal to 0 plus, all the stored energy is in the inductor. Alright, because it's carrying a current I0, the energy of course is half L I0 squared. So that energy here is going to dissipate as a function of time, and we want to find the behavior of the current and the voltage. So we have to solve this circuit. So we write equations. So of course this circuit has only one voltage and the other one is ground. So the best thing to do is to write a KCL at that node. So we write a KCL. So we said the resistor current plus the inductor current plus the capacitor current is 0. Resistor current is V by R. The capacitor current is I equal to C dV dt equal to 0. IL, we want to write IL in terms of V, right? That is nodal. We are doing nodal analysis. We want to write IL in terms of V. So first we write the equation relating V and IL. So we get V equal to L dIL by dt. We want to write IL in terms of V, but that will give us an integral, right? IL in terms of V is an integral. It's better. Eventually our goal is to find a differential equation for the circuit. So what we'll do is, rather than substituting for IL, we'll differentiate. Okay, this is what we'll do. We'll do this two ways actually. One thing, so here what we'll do is, we'll say, well, V is L dIL dt. So rather than writing IL in terms of V, let us write V in terms of IL. Then we'll do the other way also. So we say V is L dIL dt here, and then dV dt we substitute. So we differentiate this. So dV dt equal to L d2IL dt squared. And both of these we substitute in the first equation. So for V we'll get L dIL dt plus IL plus dV by dt is L d2IL dt squared. And then we rearrange so that the coefficient of the second order term is 1. Not required, but just for the heck of it. So we'll get d2IL dt squared plus 1 by RC dIL dt plus 1 by LC IL equal to 0. So this is our differential equation. Anyway, we'll keep continuing to talk about it. Or the other thing we can do, so here what we got is an equation for IL. Now let us differentiate this first equation. So we'll get dIL dt, and then for dIL dt we substitute V. So we get an equation for V. Alright, so that's here. So we have this, we differentiate this. So we get 1 by R dV dt plus dIL dt plus C d2V dt squared equal to 0. And then for dIL dt we substitute, what do you substitute? Where is it? V by L. Alright, so this becomes V by L, and then you rearrange and then divide by C and all that. So we'll get this equation. Alright, so this is the equation for V. I'm rewriting the equation for IL again. And if you look at this closely, this equation is the same differential equation for V and for IL. Alright, second order term plus 1 by RC first order plus 1 by LC into the variable. Alright, so this is actually a property of linear circuits. Okay, so before that, so this is these are both our second order differential equations, because the highest derivative in these equations is a second derivative. They are called homogeneous because the right hand side is 0, and they are called differential equations with constant coefficients because the coefficients of the IL, the DIL dt and the D2IL dt terms are constants. Alright, they could be functions of IL, then it will be a different type of equation. Alright, so these are second order homogeneous differential equations with constant coefficients, and it is a property of linear circuits that the homogeneous part of differential equations for any current or voltage in the circuit will be the same. It is the same differential equation. We can replace this V with IL, with IC, with IR. It doesn't matter. You take a larger circuit, you take many elements, as long as it's a linear circuit, you will get a differential equation which is the same for any V or any I in the circuit. Alright, this is actually the same thing we had discussed in the first order circuits, but from a slightly different perspective. But the same is of course true if it is first order, which means there is only one L or one C. But this is also true if there are many L's and many C's, as long as the circuit is linear. Alright. So what that means is that we solve this differential equation for some variable, and then the form of the solution will be valid for any voltage or current in the circuit, which is in fact what we had discussed for the first order equation. Okay, so now let us solve this differential equation. So the differential equation of this type with constant coefficients can be solved by assuming that the solution is V as a function of time. That is a solution of this differential equation. We'll assume, because people have done this a zillion times before, that the solution of this equation is of the form e raised to st. So it's a function of time, exponential function of time, where s is a constant. It is actually, as we'll see, it could be a complex number. S could be a complex number, but it is a constant. Right? So let's assume that V of t equal to e raised to st is a solution of this differential equation. If it is, then we can substitute for V in this equation and then find S from that substitution. So we say, okay, we need dV by dt and d2v dt squared. So dV by dt is S times e raised to st. The second derivative is S squared e raised to st. So we substitute all of these here, and we get S squared e raised to st plus 1 by RC S e raised to st plus 1 by LC into e raised to st equal to 0. So e raised to st becomes common, and we get this. And now e raised to st cannot be 0, so we can cancel e raised to st and we get this equation. So this is a polynomial in S. It is called the characteristic equation of the original differential equation, and this is it's a second order polynomial because it's a second order differential equation. It will be an nth order polynomial if it's an nth order differential equation. So because it's a quadratic, we know the solution of this quadratic. So we write the solution, and minus b plus minus square root b squared minus 4ac divided by 2. So I've taken the 2 up, and this is the form we'll get. Alright, so we get two values of s. It's a quadratic, so we get two values of s. So how do we write V of t then? The most general answer, so this is a mathematical statement, not proving again, you'll probably prove it in the maths course this semester, is that V of t can be written as a linear combination of the two possible solutions, because we have two solutions, right? E raised to s1t and e raised to s2t are the two possible solutions of V of t. The general solution is the sum of these with some arbitrary constants a and b. Alright, so we have two constants. These are also sometimes called integration constants, because in some theoretical way this is a second order derivative. So if we integrate this twice, then we can get v, and when we integrate when we do an integration twice, we'll get two integration constants. So these are also thought of as integration constants, which now we must find. Alright, so we have the solution. We now know that the solution is of this form, but we must find a and b to complete the solution. So how do we find a and b? The way we find is from initial conditions. Alright, so we need two initial conditions to find the two constants a and b. So what are these initial conditions? That one initial condition is obvious. We want to know the voltage at t equal to 0 plus, and that will give us one condition. The other condition is the derivative of this voltage at t equal to 0 plus. Okay, so this is what we need, and I'm just telling you again why, how, all that in mathematics. We need to know these two. Once we know these two, we'll be able to find a and b. Alright, so we need to determine, we already know v at t equal to 0 plus, we've already found it, it was 0. So we say v at t equal to 0 plus is 0, and we substitute that here. So this is just a plus b at t equal to 0. So we'll get a plus b equal to 0, and therefore b is equal to minus a. So that is one equation. The other equation is we need to determine dv by dt at t equal to 0 plus. How do we? Well, we are able to, because we know that dv by dt is related to the capacitor current. Currents we know, derivatives we need to relate to currents. Alright, so we say dv by dt at t equal to 0 plus is equal to IC at t equal to 0 plus divided by C, and we have already found IC at t equal to 0 plus. If you recall, it was minus I0. So we say minus I0 is C dv by dt at t equal to 0 plus, and that we substitute here. So we find the derivative of this. So here C multiplied by the derivative of this, which is a e raised to s1 e raised to s1t plus s2b e raised to s2t at t equal to 0 plus. And then, so the exponential terms go away, and so we'll get C into S1A plus S2B equal to minus I0. And A is equal to minus B. So putting it all together, we'll get minus I0 divided by C equal to A into S1 minus S2. So we've determined A, and of course, therefore, B also. So this is how we find. Alright, this is how we find the constants A and B. We find we would have already determined from a solution at t equal to 0 plus one voltage and one current. Alright, and we'll use that information to find the specific voltage and the derivative of that voltage at t equal to 0 plus, and we'll substitute that here to find A and B. Okay, so now this is it, and now so we say A equal to minus B equal to all this. And so we write the final solution. So we say V of t is equal to I0 by C S2 minus S1 e raised to S1t minus e raised to S2t. Please check dimensions. I have assumed, or I have not bothered about dimensions. You please check. So what is S1? Let's go back. S1 is here, yeah. So S1 is all this. So check that S1t is dimensionless. Alright, it's straightforward, but make sure and convince yourself that S1t is dimensionless, number one. Number two, I0 over C into S has the dimensions of voltage, right? This is e raised to something is dimensionless, so this must have the dimensions of voltage. The reason for this is of course very straightforward. I hope you will do this in 30 seconds, but the point for emphasizing this is that when you are actually solving, you keep checking dimensions, because if you made a mistake, the dimensions will not come out correct. Alright, so this is our solution now. We know I0 is given to us C is given to us, S2, S1 we can find from R, C and L values. So everything is known, alright. But the solution is still not complete. Why is it not complete? Because these roots of these two equations can possibly be real, or they can be equal, or they can be complex depending on the values of R, L and C, right? If this quantity under the square root is negative, we'll get complex roots, and then this needs a special treatment. So let us go through each of these cases. We'll start with the real. So case 1 is if the roots are real, which means that this first term is greater than the second term, then they are real. Now let's do a numerical example just to go through this process. So let us say the values of R, C and L and I0 are given to us. Then we find each of these terms. So 1 by 2 RC. I'm just going through this. You please do this yourself. So if you calculate 1 by 2 RC, you will get 10 raised to 6. So 1 by 2 RC, the whole squared is 10 raised to 12. That is under the square root. 1 by LC turns out to be 5 times 10 raised to 11. So that is less than 10 raised to 12. So the square root is positive. And then we put all of this together and find S1 and S2. By the way, I mentioned this somewhere, I forget where. Yeah, both the roots must always be negative. Alright, when the roots are real, the roots must be negative. Why? You think about it, okay? S1 and S2 must always be negative numbers. You please think and make sure that you are convinced that they must be negative. Again, the reason to emphasize is in case you end up with a positive number, then you must stop. Alarm bell must go up saying, no, I have done something wrong. They cannot be positive. They have to be negative. Okay, so we get S1 equal to something, S2 equal to something, S2 minus S1 equal to something. We substitute all of this in V of t and we'll get an expression for V of t, which can be written as e raised to minus s, or it can be written as t divided by something, because that tells us the time constant. Often we are interested in the two time constants of the circuit. So of course, first of all, there are two time constants here, because time constants are physically more easy to visualize. Alright, so what I'd like you to do is, I'd like you to pause this video and plot V of t. Okay, this is, as I had said earlier, it is important for you to learn to plot these things, not just as an exercise, but because to visualize these voltages and currents is a very important thing when you are handling and learning and trying to understand circuits. Alright, so pause the video and plot. Okay, I'm continuing. So the way one plots this is one plots each of these terms. So this constant is there and then there are two exponentials. So one plots the two exponentials individually and then adds them. So we have one in the first exponential is some number e raised to minus t by a time constant, and the second is minus that same number e raised to minus t by another time constant. First of all, V2, the time constant, is larger. A larger time constant means it will move, it will decay slower. Alright, it is negative. V1 is positive and faster. So V1, both of them at t equal to 0 have a value plus 0.94 and minus 0.94. So V1 starts out at plus 0.94. V2 starts out at minus 0.94. V1 decays exponentially. It decays faster than V2. V2 decays slower. It is always negative. So V2 is negative. Alright. The sum of these two, if you think about it, will always be negative because of the fact, well, of course, at t equal to 0, the sum is exactly 0 because both of them are equal and opposite. But anything greater than 0, because this time constant is larger, the value, the magnitude of V2 will always be larger than the magnitude of V1. Alright, so at any point in time, this magnitude is larger than this magnitude. So this minus this will always be negative. That's the second thing we notice. The third thing is at t equal to infinity, V has to go to 0. Alright, so V starts out at 0. Eventually it must go to 0. And in between it is always negative. So we can guess that it has to have this form. It has to increase, then it has to decrease back to 0. So this is the shape of V. Alright, why is it negative? So you look at, let me see. So if you look at this circuit, current IL was flowing here. Initially at t equal to 0, there was a current. This capacitor was not charged. Now this current will flow partially into the capacitor, partially into the resistor, but the current will basically keep flowing in the counterclockwise direction for this mesh. Therefore, the capacitor is charging with a current flowing up, which means the voltage here is positive with respect to the voltage here, which means that V is negative. Alright, so we found VC. Now that we were asked to find, V, which is VC, we are also asked to find IC and IL for the circuit. Now we found V, and we know that C is equal to simply C dV by dt. So we simply differentiate V with respect to time and multiply by C. C is already here. So we get IC equal to, forget the C, dV by, so this C is not there. This C is not there, that goes away. And the C is here actually. Right, so I is C dV dt. Alright, so that's an easy expression. I would like you to, it's a good idea if you spend a few minutes plotting this, alright. That you do at home. The next is, how do we find IL? Alright, we know V, we know IC, how do we find IL? Pause, think 2 minutes, or actually find IL if you are able to. I'm not able to, spend some time finding IL. Alright, I will continue. Now I'm switching to handwritten, but because I discovered that it is taking just way too much time to type, so I should tell you that this is the 14th slide. So about 12 slides I had to type of equations. It took me 4 hours. So that is, I'm not able to spend that kind of time. So I'm not typing. This handwriting is much easier. Okay, finding IL, there are actually 2 ways. The easier method is KCL, IL plus IC plus IR is 0. So IL is minus IC minus V by R. We already found IC. We know V already. So we just put all of it together and write big expressions, but it is very straightforward. There is another method, which is, we know that V is equal to L dIL by dt. So we can integrate this equation to find IL. We know V, so we can integrate to find IL. Of course, this method and this method should give the same answer, but it is instructive to integrate to kind of, okay, let's just go through this very quickly. So we say IL is equal to 1 by L, 0 to t, V of t dt plus IL at t equal to 0, because it's a definite integral. And then, so we substitute for V, which is I0 by C S2 minus S1 e raised to something. And IL at t equal to 0 was I0. We already know that from our original initial solution. And then we integrate. So this is the integral. This is the integral. And you know how to integrate this. So we get this. Alright, so IL, we get this. What do we find here? What we find here is that there is a constant. Alright, but we know that IL at t equal to infinity must go to 0. The exponential terms will both go to 0. which means that this constant term is going to turn out to be 0 when you substitute everything, S1, S2, etc., etc. It must go to 0. Alright, so make sure that it does go to 0. Alright, yeah, that is all. Okay, let us do case 2, which is the roots are equal. So case 1 was the roots are positive. When are the roots equal? The roots are equal when the square root is 0. If the square root is 0, then S1, S2 both are minus 1 by 2 RC. And that happens when this condition is satisfied, right? When this is 0. Now for this condition to be satisfied, the R, C and L values must be such that this equality is exactly obtained. Now it turns out that in real life, it is practically impossible that the capacitor, inductor and resistor values are so precisely matched that this equality is achieved. Alright, the reason is whatever one does to attain a exact equality implies exact 100% accuracy of inductor, resistor, capacitor values. Now that never happens in practice. Alright, first of all, because one can never obtain 100% accurate values of components. I cannot go to SP Road and tell them give me a resistor of 100 ohms and it should be exactly 100 ohms. It cannot be 100.005 also. It's not possible. Most resistors are 5% accuracy and so are inductors and capacitors. That is one. Now suppose by chance, by fluke, the RLC values turn out to be equal. Then what happens is when you put them in a circuit and currents are flowing and voltages are appearing, resistors will heat up. And when resistors heat up, the resistance changes. Little bit, but it changes. And even a little change will make this equality invalid. Alright, so from an engineering perspective, we don't deal with this case at all. We say either the roots are real or they are complex. They are never equal. In mathematics, you will study this because that's what mathematicians do. So in fact, the way to find the complete solution for the voltage Vt when the roots are equal is it's a whole different method you have to use, which you will do in mathematics. In circuits, we don't bother about this case. Alright, so I'm not going to discuss this case. We'll go straight to the third case, which is of course a very important case, and as I said, in communication circuits, the parallel RLC circuit is very common, and in a communication application, the roots are always designed to be complex. Alright, so what does complex mean? That the expression under the square root is negative. Now let's define a couple of terms. Let's say alpha is 1 by 2 RC, and let us say omega naught squared is 1 by LC. Alpha is called the damping factor and omega naught is called the resonance frequency. So again, you can convince yourself that 1 by LC has the dimensions of frequency squared. Alright, that's why the square is there. And therefore, then one can write S1, S2 as minus alpha plus minus square root alpha squared minus omega naught squared. And the roots will be complex when alpha is less than omega naught. Alright, so let us define omega d squared as omega naught squared minus alpha squared, the negative of this square root. Alright, so that of course this quantity now is positive, so we can represent it as the square of a real number. Omega d is a real number. And so we'll say S1, S2 is all this, where minus omega d squared, right? Because omega d is a positive number, under the square root is negative. And so we can write this as minus alpha plus minus j omega d, where j is square root of minus 1. Okay, so now I must tell you that now that you are electrical engineers or electronics and communication engineers, you have to get used to this idea of minus square root of minus 1 being called j. Alright, because mathematicians called it I, but in parallel, historically, electrical engineers were calling currents as I. I really don't know how it became I. That somebody will have to look up history and see. But in any case, for the last 200 or more years, current is called I. But square root of minus 1 is also called I. So electrical engineers, of course, don't want to change their terminology. So they kept I for current, and so they had to call some square root of minus 1 something else. So they have called it J. Alright. So when you do electrical circuits, you must get used to J for square root of minus 1. Okay. Don't use I. If I see I will cut marks. Alright, over a period of time you will get used to it, but you have to start getting used to it from now on. Alright, so anyway, so S1, S2 is all this. So we say, okay, V of t is some constant e raised to S12, S2t, and S1 is all this complex number, S2 is another complex number. And so we take e raised to minus alpha out, and we get e raised to j omega, e raised to minus j omega. Alright. Now this is V of t. Now this is weird. If you think about it, this is a very weird mathematical expression, because what this is telling us is that the voltage appearing in that real RLC circuit which we can build in the lab, that voltage seems to be a complex number. But that doesn't make any sense, because voltages in real circuits cannot be complex. They are numbers, they are real numbers. So something is missing. So let us do more mathematics and figure out how we can remove this weirdness. Alright, so okay, so this is what we'll do. So we know that e raised to j something can be written as cos something plus j sin something. These are Euler's identities. You are familiar with these. So cos plus j, cos minus j. So we substitute for e raised to j something here and for e raised to minus j something here in terms of cos and sin. And then we combine the cos terms and sin terms. So we'll get V as e raised to minus alpha t a plus b cos omega dt plus j a minus b sin omega dt. Now a plus b is a constant, so let us call a plus b as a1. And j into a minus b is another constant, and let us call that constant b1. Alright. Now it turns out, and I will not prove this, a lot of things I am not proving. It turns out that A1 and B1 are real numbers. Alright, magic. So what will happen is, if you were to go through the actual solution in terms of these, then you will find that A and B both will be imaginary only, not complex, they will be imaginary. So they both will be j something, so and then the jj will become j squared equal to minus 1, and the j will disappear. Alright, it can be proved if you go through the algebra from here and solve the circuit in terms of the j's. I am not doing it. The point is, if the roots are complex, then the solution for V of t can be written in this form, which is different from this form. This form causes problems with j's. You write it in this form, everything is real. Alright, so V of t is e raised to minus alpha t into a1 cos omega dt plus b1 sin omega dt. So this is a form of the solution if the roots are complex. So this is what you will do. So when you are solving a circuit, the first thing you will do is you will find the roots. Well, you will write the differential equation, you will write the characteristic equation, you will find the roots. If the roots are real, you use this form of the solution. If the roots are complex, you use this form of the solution. Alright, please remember this, very, very important. Alright, having arrived at the solution, we of course need to find a1 and b1 again from the same initial conditions. All right, the process is the same now as we did before. We have two unknowns, we need two initial conditions, same thing. So we say V at t equal to 0 plus is 0, the capacitor current at t equal to 0 plus is minus I0, and that current can be written as C dV dt. And so we have, okay, so if you put V equal to at t equal to 0 is 0, so we'll get 0 equal to, this is 1, this is cos 0 is 1, so we'll get A1, and plus sine 0 is 0, so nothing. So we'll get A1 on the right side, 0 on the left side. So we get A1 equal to 0, it goes away, and then we have to find B1 from this condition. So we say without A1 we can write V of t as e raised to minus alpha t, B1 sine omega dt. Then we say dV dt at t equal to 0 when equal to minus I0. So we get dV by dt, we differentiate this and put t equal to 0. Alright, so we differentiate this, we get this, sine cos e raised to alpha, all that, t equal to 0. This goes away at t equal to 0, this stays, omega d, only omega d stays, so we'll get minus I0 by C equal to B1 omega d, so we get B1. Alright, again a negative sign, you see the negative sign, that is because of that current flowing upwards. Of course, this is more complicated because this current is actually going to go positive and negative. Alright, so this is a final expression for the voltage in this circuit if the roots are complex. Some constant, negative sign, e raised to minus alpha t sine. So this voltage, pause and plot. Okay, pause the video, plot this voltage. Okay, I continue. This is a plot. This is a plot. The voltage starts out at some negative value and it oscillates because it's a sinusoid. This is a sinusoid, but the envelope is the exponential. The envelope is e raised to minus alpha t. So the output is a sinusoid that decays with time. Eventually the voltage will go to 0, but it's going to oscillate a lot before going to 0. And this is called an underdamped. Okay, let me see. Okay, let me talk about underdamped and overdamped. So you're familiar with, I'm not sure if you're familiar with underdamped, overdamped from a spring and mass analogy in 12th standard and JEE physics. So if you have a spring and a mass is attached to it, and if I pull the mass and leave it, that mass will go up and down, up and down, up and down, and eventually settle down to 0. If I were to plot the displacement of that mass as a function of time, it will be a sinusoid, and but the sinusoid will slowly, the displacement will slowly reduce because of friction in the system, and eventually the mass will stop moving and the displacement will become 0, which is at t equal to infinity. Now imagine that this mass is placed in a big tub of very thick oil. Alright, and now somehow I managed to pull the mass and leave it. Now if the oil is very thick, the mass will probably just slowly move and go back to its original position, but will not oscillate. Alright, because if there is too much friction, oscillation will not occur. That case is called overdamped. Alright, so overdamped means there are no oscillation, there is a lot of damping. What does damping mean? Lot of friction in mechanical systems. In electrical systems, it means, where is it? Where is the circuit? Here. If this resistance is such that it provides a lot of loss, alright, loss implies this is the equivalent of friction, then the system will be overdamped. And in a parallel circuit, if the resistance is small, it implies a lot of loss. Small, why? Because a small resistance means that a large fraction of this IL will flow through R and a small fraction through C, and that current will keep getting, or the energy will keep getting lost as heat in the resistor. Now imagine a case where this R is large. Well, let us imagine a case where the R is infinite. Okay, it's not there. Infinite means open circuit, it is not there. Same circuit, let's remove the R. And if we had some initial current flowing in the inductor due to that current source, and we remove the current source at t equal to 0, that current, that energy will go to the capacitor, and that will come back to the inductor, and it will go to the capacitor, and it will go to the inductor. It has no place to get lost because there is no friction equivalent. There is no loss of energy. The resistor is what loses energy. Okay, so let's look at that case here. Okay, so here is a numerical case. So this is the same circuit. This is our equation we derived, all this. Now let us consider the case that R is infinite. Alright, so there is no R here. If R is infinite, so let's look at these equations. If R is infinite, alpha becomes 0. Alpha becomes 0, the exponential term becomes 1. Alright, this goes away, it is just a 1. Alpha becomes 0, this alpha becomes 0, omega d is 1 by LC and some value, and so V of t is minus 2 sine omega d t. It is a pure sinusoid. So the equivalent of the mass and spring is, you pull the mass, you leave it, there is no friction. With no friction, that mass will keep on oscillating forever and ever and ever. It will never stop because no energy is getting lost anywhere. Similarly here, so there in a mass, as the mass goes up and down, as you know, what is happening is the energy is getting transferred between potential and kinetic. Alright, at the extreme position, the energy is all potential. At its resting position, the energy is all kinetic. Alright, the energy keeps going back and forth between potential and kinetic. In an electrical circuit, the energy keeps oscillating between magnetic energy in the inductor and electrostatic energy in the capacitor. It keeps oscillating back and forth forever and ever for an infinite resistor. So for a parallel RLC circuit, an infinite resistance means an ideal case. Anything less than infinite, the resistor would dissipate energy, and the lower the value of the resistance, the higher is the damping. Alright, the lower the R, the higher the alpha, the more is the decay. Alright, so that is that. So case 2 is R equal to 20. I would like you to write the equations and plot V of t just as an exercise. Alright, so that is the end of this lecture. We'll continue with RLC circuits next time.